Hello everyone. We'll wait for 2-3 more minutes and then we'll start the session. Yes, I hope my screen is visible. And just can somebody raise your hand and let me know if my screen is visible or put it in the chat. I've shared my screen, so is it visible to you? And also if I'm audible or not, can you also let me know? Yeah, okay. Sudeep and Satish have given me a thumbs up, so I hope my screen is visible and I'm audible as well. Uh, just in case, just to check, I'll allow the mic of Satish. Satish, I have allowed your mic. Can you unmute yourself and
Yeah,
tell? Yeah,
yes,
I'm
yes.
audible and
Screen
my
is visible, you are audible.
okay, and my slides are also changing, right?
Yes, yes, yes.
Okay, thank you. Okay, uh, thank you, Dr. Satish. Is anybody else coming, or shall we get started? It's almost 6:14. We'll wait for one more minute and we'll get started. All right. Hello, everyone. Welcome to the weekly discussion doubt clearing session 2 of the course Maintenance and Repair of Concrete Structures, NOC23-CE06, which is taken by Professor Radhakrishna G. Pillai of IIT Madras on NPTEL. And I am Ashirvad Satpathy. I am a PMRF research scholar from IIT Delhi, and I am one of the assigned teaching assistants of this NPTEL course. What I do is I take weekly sessions of in which we discuss the questions and answers of the assignment questions that have been given to you in the previous weeks, which you have already submitted the answers of, and we also try to clear some of your doubts that you might be having related to the lectures of the last week. There is another teaching assistant of this course. His name is Umesh. He usually takes his sessions on Fridays from 7 to 9 p.m. And I take these weekly sessions on Saturdays from 6 to 8 p.m. Before I proceed to the session of today, I'll also like to mention that I have put the link of the last recorded lecture of session 1 in the chat. So it is uploaded on YouTube. You guys can access it if you want to revisit the lecture, or if some of you have missed it. Apart from that, I have also put the link of the folder where I have uploaded the slides of the previous presentation of the last week session. So you can also go and check that. And the link of that folder will remain same for the duration of this course. So whenever I conduct any kind of sessions, I'll be uploading these. Let's say the lecture slides of today's session. I'll also upload these slides into that same folder link. So that folder link will remain same, and also the YouTube channel will remain same. So you can go and access as many times as you want. All right, let's get started. This is session 2, and today we'll be discussing the week 1 assignment 1 questions. There are 10 questions of related to the week 1 lectures, and also we'll try to clear some of your doubts of week 1 lectures. Last time also we had taken some doubts of week 1 lectures. I remember some of you asking some questions related to hydrogen embrittlement. In case you are present today, please raise your hand at the end. So we'll be again discussing that. And and in case some of you were not present in the session 1, we'll again take up your doubts related to week 1 lectures. The further week 2 and week 3 lecture doubts will be taken up in the upcoming week. All right. Proceeding to question number 1, which was why the steel embedded in uncontaminated concrete does not corrode. The question 1 was this, and the options given were due to the presence of CSH gel in concrete, due to the high pH of the concrete pore solution, due to the formation of a passive layer over the steel surface, due to the presence of the moisture inside the concrete. Okay, I'll quickly go to the meeting, and can somebody uh, do you want to answer to this question? If you want to answer your questions, or if you want to speak something in the due course of this section, then please raise your hand in the meeting so that I'll allow your mic and you can unmute yourself and speak. All right? Who wants to answer this question? Okay. I guess I have also allowed your cameras. I've allowed your videos. You can turn on your videos if you want. Uh, Dr. Satish has given me a thumbs up. You can raise your hand, I guess, but I'll allow your mic. I've allowed your mic, Dr. Satish. You can unmute yourself and speak.
Am I audible?
Yes, yes, Dr. Satish.
Uh, uh, Answers are two. Firstly, due to high pH of concrete pore solution,
Okay,
which is of the order of 12.5, 13 or so. And then second reason is due to formation of a thin passive layer over the steel surface.
Right. So, sorry. Yes. Thank you, Dr. Satish. You have rightly pointed it out. So, yeah, the answer to this question is due to the presence of high pH in the concrete pore solution and due to the formation of a passive layer over the steel surface. So I'd also like to ask this question: why do you think a high pH of the concrete pore solution helps in um, restricting or preventing corrosion from happening? And also the second also about the second, same thing about the second statement. That is, how does why does the passive layer and what is the passive layer and how does it help us from preventing corrosion? Can somebody also answer to this? Yes, you guys can raise your hands. Let's keep it
Yes, yes.
interactive. Okay, yes, Dr. Satish, go ahead.
So this passive layer that protects,
Hmm.
because that is the interface between the steel reinforcement and environment around. And
Right.
then this alkaline environment always provides protection. pH of the
Hmm.
odor 10, 11, or 12 uh, is helpful in resisting uh, attack of corrosion.
Right. Thank you, Dr. Satish. So, typically what happens is, in case of a steel reinforcement, let's say this is a steel reinforcement which has some ribs. So the steel reinforcement has a passivating layer around it. What happens essentially is that the steel or the metal uh, forms some oxides when it comes with contact with the surrounding environment, and these oxides are which also can be called as the um, initial corrosion products. So this initial corrosion products form over the around the surface of the uh, steel rebar, and they provide us kind of a coating around the steel rebar. So this is I've just shown uh, a longitudinal section of the rebar. So this is the passivating film or layer that forms around the steel rebar, which is formed by the initial corrosion products or the oxidation of the metal, right? So these are the metal oxides. So they provide kind of a coating outside the steel rebar, which protects the steel from interacting with the surrounding environment. So for any iron to attack the metal or the steel, it has to first break the passivating film, and then only it can corrode the steel reinforcement. For example, we had seen this same case in case of chlorides, and it also happens in the case of carbonation-induced corrosion as well. Once the pH is decreased, if the pH decreases, the passivating film is unstable. So this passivating film gets broken, and due to that, corrosion might happen. So a high pH of concrete pore solution is good for to restrict the corrosion of strain, and the formation of a passive layer also protects the seal from getting corroded. All right. Moving ahead to the next question. The second question was, what are the typical characteristics of carbonation of concrete? And the options were embedded steel usually experiences localized or pitting corrosion, and this was related to carbonation of steel. Sorry. Yeah, this is related to the carbonation of steel. So carbonation of concrete. So what are the typical characteristics of that? Embedded steel usually experiences a localized or pitting corrosion. Carbonation is severe When the relative humidity is around 60 to 70%, carbonation becomes more severe when temperature decreases, or pH decreases when the concrete undergoes carbonation. Which of these are correct? Can somebody answer to this question?
Again, answers are two.
Dr. Satish, I would like for somebody else to answer. Thank you for,
Right, right,
yeah, if somebody else doesn't answer, I'll give you a chance. Thank you.
right, right.
Yes, uh, anybody else wants to answer to that question? I can see there are 5 attendees to the session. Aishwarya, Kiran, Manisha, Sudeep. Dr. Satish is the usual suspect who answers to the all the questions. Yes, any of you wants to answer to that question? I hope you have attended the you have watched the lectures. All right, let's not waste any time. Dr. Satish, go ahead. Yeah, I'll unmute. I'll allow your mic. Yes, go ahead.
Uh, Satpathy ji, actually, I got doctorate from IIT Madras in the same subject 10 years
Oh, okay.
before Dr. Pillai.
Oh, okay,
Now I'm
okay.
a professor. I'm a retired commissioner cum secretary from Government of India. Now I'm in academics. So
Oh,
this will be my ninth certificate. I already acquired nine.
okay, great.
Okay, coming
Nice to
back to
know.
this question, uh, this localized pitting normally takes place in case of chloride attack, so it
Right.
cannot be the answer. And that a lot of studies have been done relating to relative humidity. 62%, 70% is quite conducive for carbonation. So
Mm-hmm.
second one is correct. Then this pH comes down below 9 when concrete undergoes carbonation. So answers are two, second and fourth.
Right. Ah,
Temperature
okay.
decrease probably may not be the answer.
Right. Okay. Yes. So thank you, Dr. Satish. You rightly said it. Uh, so the answer to this question is the second and the fourth option, as he has already mentioned. Firstly, I'll discuss all these options one by one. Localized pitting and corrosion, as Dr. Satish also mentioned, it happens in the generally or usually in the case of chloride-induced corrosion. So the chlorides, as we have also discussed in the last class, the chlorides attack the particular region of the reinforcing bar, and in which in the pit becomes an anode, and the surface of the steel becomes a cathode, and this cathodic and anodic reactions take place, and the corrosion products are formed. And again, HCl is formed, and uh, uh, the pH is reduced, and this gives a vigorous process. This gives rise to a vigorous process of the pitting corrosion. So essentially, the pit gets deepened, and the reinforcing steel corrodes at a at a particular location, and is and this the reinforcing steel is no more in a serviceable condition. It breaks. So yeah, this kind of this so this is not in the case of carbonation induced corrosion, but yeah, not for carbonation or usually in chloride corrosion. But suppose this is a concrete surface, and this is another concrete surface. I mean, this is a concrete surface with a surface crack on it. Then if there is a presence of crack, the carbonation can be rather localized instead of more compared to this. Let's say this is a cross section of a concrete element. The carbonation in this would be kind of uniform all around. The carbonation depth will be uniform all around, right? But if we compare it to a cracked concrete, the carbonation would be more localized. because due to the presence of cracks, the carbon dioxide can get easily diffused, and carbon dioxide and what humidity, so both can get dif- um inside the pores of the concrete. So the if this is the case of the carbonation depth or around the concrete, at the localized crack, it might be a little higher. So, but anyway, in any case, this might lead to a pitting kind of a corrosion sometimes, but it is very rare. So, usually, talking about pitting corrosion, it is related to chloride-induced corrosion. Second statement, which is correct, is carbonation is severe when the relative humidity is 60 to 70%. And to explain this, I'll take the help of one of the charts given by Bertolini et al. In 2013. This is a good book for corrosion. And you can see this graph represents the carbonation rate versus the relative humidity inside the concrete microstructure. And you can see that between 60 to 70%, 60 to 80%, the carbonation rate of carbonation is highest. And this happens, so this usually happens because, see, beyond 80%, the pores are saturated. And we know that for carbonation to occur, carbon dioxide has to get into the concrete pores, right? And if the pores are saturated, the diffusion of carbon dioxide is less, decreases. The carbon dioxide diffusion decreases because the solubility of carbon dioxide in water is less. So beyond 80%, when the pores are saturated, the carbon dioxide cannot get inside the concrete. And when the relative humidity is less than 60%, what would happen is that the concrete is dry. So even if carbon dioxide can get into it, but there is no the pore solution or the water that is essential for the ionization of the hydration products, because for carbonation, the hydration products like Portland egg, it gets carbonated. So the for the reaction to take place, the carbon dioxide gets diffused in the concrete, and it has to first form a carbonic acid. This carbonic acid gets reacted with the reserve alkalinity or Portlandate or whatever the alkaline products, hydration products that are present inside the concrete, and then only the carbonation can occur. The alkalinity will get decreased. So in case of dry pores, even if CO2 can get inside the concrete, the carbonation reactions cannot take place. All right. So this is the ideal range in which the maximum rate of carbonation is usually found in concrete structures. So that answers the second statement related to this question. The third was carbonation becomes more severe when temperature decreases. As we know that this is from the diffusion laws of diffusion, that when the with the increase in temperature, the diffusion also rate of diffusion also increases for gases. And so I mean, so this is not a right statement, because carbonation will be more severe when the temperature is increasing, provided there is sufficient relative humidity available. And lastly, the last statement was pH decreases when the concrete undergoes carbonation. This is true because the alkalinity gets consumed, so the pH will decrease. Okay, moving on to the third question. Which of the following statements about chloride threshold is or are correct? It depends only on the steel. It depends only on the cementitious systems. It is a function of both steel and cementitious system. It can be increased by using corrosion inhibitors. It can be decreased by using corrosion inhibitors. Will somebody answer to this question? Please raise your hand so that I'll let you unmute yourself and speak.
Should I answer this question?
Yes, yes, Dr. Satish, go ahead.
You know, question is chloride threshold.
Yes.
Uh, it's a function of both steel and cementitious system.
Mhm.
Then it can be increased by using corrosion inhibitors.
Okay.
But
So
I
you
think
want
these
to say that
two
the
answers are
third,
there.
okay. Also, okay, thank you, Dr. Satish. Also, can you tell me what is chloride threshold and I mean,
You know,
why,
the
how, what is
uh,
it related to the
up
uh,
up
deterioration
to
of concrete or steel?
the extent of chlorides which can be uh, borne by the system uh, before corrosion is initiated.
Okay,
Once it is initiated, then it's very difficult to stop the process.
right.
That level is probably chloride threshold.
Okay, right. Thank you, Dr. Satish. Yes, as he has rightly pointed out, the answer to this question is it is a function of chloride threshold is a function of, sorry, of both steel and cementitious system, and it can be increased by corrosion using corrosion inhibitors. Firstly, chloride threshold, as Dr. Satish has already told, it is it chloride threshold usually indicates the amount of chlorides that that can get accumulated at a certain location near the reinforcing bar, which will be sufficient to break the depassivating film of the rebar, right? So that is the amount of, so chloride threshold is basically a certain amount of chloride that will be required or that will be sufficient enough to break the depassivating film of the rebar. Now, once the depassivating film of the rebar is broken, so see, for a structure which has a higher chloride threshold, what will happen is that, let's say, um, I'm not exactly a structure. This is a rebar inside a concrete system, right? And this is one system one. This is another system, and this is another rebar inside it, and this is system two. Let's say the chloride threshold of 2 is greater than 1, right? So what will happen is that the amount of chloride that system 1 can take before the depassivating film breaks will be less than that of the amount of chloride that system 2 can break. So basically, if this is the Cl minus, so higher amount of Cl minus can get inside it and get accumulated before it gets it breaks the depassivating film, as compared to in case of 1, less amount of chlorides can still be sufficient to break the depassivating film of the rebar. And so this is what is chloride threshold. So once the depassivating film is broken, as you also might have seen in the lectures as well, once the depassivating film of the rebar is broken, it is prone to corrosion now. So that will be an initiation phase wherein there is no corrosion is happening, but it is in process. Once it start getting corroded, that will be the propagation phase. And beyond the propagation phase will
once the I mean the threshold damage level is crossed, will have to provide certain repair or rehabilitation measures to the structure. So, uh, so basically, the chloride threshold is related to also uh, to lengthening the initiation phase. So, chloride threshold is if the chloride threshold of a system increases, this essentially means that the initiation phase is longer. So this means that uh, system 2 will have a higher initiation phase or a longer duration of initiation phase rather than system 1. So now this is about chloride threshold. So chloride threshold not only depends on the type of steel. Of course, I mean there are there are certain steel types in which the chloride threshold is high as compared to other steel types. Like for steel with higher carbon content, the chloride threshold is low. For stainless steel, which has alloys and which has different kinds of alloys, the chloride threshold is high. So it depends on the steel, but not just on steel. It also depends on the type of the cementitious materials that is being used in the system. So so it is the chloride threshold is a function of both steel and cementitious system. Apart from this, it can be increased by use of corrosion inhibitors. So corrosion inhibitors are certain admixture compounds. Sorry. Yes. Just give me a moment. Yes. So corrosion inhibitors are certain chemical admixtures that are added to the concrete while mixing it. And these corrosion inhibitors, so there are like typically bipolar corrosion inhibitors, as you have also already seen in the lectures as well. What they do is they not only prevent the site of pitting, which is anodic site, they also, I mean, they also protect the both the sides, the cathodic as well as the anodic sides, by getting diffused in the depacivating film and strengthening it. So the use of corrosion inhibitors will also lengthen or increase the initiation period of the corrosion, and it will also increase the threshold, the chloride threshold. So, yeah, so these are the answers to this question. Sorry for taking your time. Yeah, moving ahead to the next question. Question 4 is the service life of a structure exposed to chlorides depends on surface chloride concentration, pH threshold of the concrete, chloride threshold of the steel concrete system, chloride diffusion coefficient of the cover concrete. Anybody wants to answer to this question? Anybody else except from Dr. Satish? Nobody? Manisha, Kiran, Aishwarya? Let's keep this session interactive, guys, so that uh, we'll have a fruitful discussion, as well as both of us, both myself and all the attendees will learn something from this lecture sessions. All right. Dr. Satish, I have allowed your mic.
Yes. Chloride diffusion coefficient is a factor because cover crete area is very, very important.
Mm-hmm.
Then chloride threshold has to be a factor because that decides uh, that is related with the uh, time and chloride concentration also.
Mm-hmm.
Then surface chloride concentration also matters because if there are more chlorides on the surface, then obviously there will be more intrusion of chlorides. So answers are three.
Okay, you want to say that chloride diffusion coefficient of the cover concrete, okay. Chloride
Yeah,
threshold
yeah,
of the steel concrete system, that is fine. You also want to say that surface
yes,
chloride concentration will also affect the service life of a structure exposed to chlorides.
yes.
Okay, and why would you say that? Okay, let's go one
Uh,
by one.
but
Chloride diffusion coefficient, how does it?
suppose,
Yeah.
suppose there is extreme case that there is no chloride concentration on the surface, so there is nothing to intrude into concrete.
Okay.
So as chloride concentration increases, then only the case arises of breaking the film and affecting corrosion process.
All right. No, let's go one by one. Chloride diffusion coefficient of the cover concrete. How does it affect the service life of a structure exposed to chlorides? Can you tell me that?
In case diffusion coefficient is high,
Uh-huh.
then uh, then related to time factor, there will be more of chlorides after
Right,
a certain time
right,
because this diffusion coefficient has something to do with element of time,
right. So higher the
and we are
diffusion
talking about
coefficient,
service life. Yeah,
the chloride penetration resistance of the of the concrete reduces. So the penetration resistance reduces once the diffusion coefficient is higher. Okay, all right. Talking about chloride threshold, we already know that. We have also discussed it in the previous question. Chloride threshold increases, then the initiation phase will get longer, and hence the service life of a structure will be increased, right? But coming to what Dr. Satish has mentioned, the answer to this question will actually be third and fourth, and not surface chloride concentration. As I mentioned mm, in the last slide, in the last question as well, surface chloride concentration has nothing to do with the inside the corrosion process of the structure. So essentially what happens is that whenever there is a chloride, of course, I mean, if comparing between a structure that is exposed to surface chlorides and a structure which is not at all exposed to surface chlorides, yes, there will be a possibility of higher, there will be a higher possibility of corrosion in the case of the structure that is exposed to chlorides. But assuming that there is sufficient cover, and if the chlorides can, and if the chloride threshold is sufficiently high for the service life of the structure to be well consumed, and for the structure to remain serviceable throughout its design life, then I don't think the surface chloride concentration will make a difference to the corrosion process. So the basically what
uh,
happens, as I also yes, Dr. Satish, you want to say something,
uh, if we have a look at the answers,
right?
probably surface chloride concentration has been given as the correct answer. You know, on eighth evaluation has been done. There they
Okay,
say that this is the correct answer. Kindly have a look at the answers provided by NPTEL.
all right. I'll have a look, but I think okay. I'll if you, I mean,
Just,
yes,
just,
again,
just, just recheck. Just recheck
okay,
the answers given on eighth midnight. They say that this is one of the answers.
Okay,
if
I'll
I
check
remember
again.
correct. Yeah.
All right, I'll check again. But anyway, what I want to mention is that it is a so once the chlorides get inside this the concrete matrix, they get accumulated on the rebar locations, on certain rebar locations. But corrosion will not take place until the depassivating film is broken, and that depassivating film is related to the chloride threshold. So if the surface chloride concentration is if the chloride concentration is low inside the concrete, even if the surface chloride concentration might be high, but the diffusion is low, and hence the surface chloride concentration hence the chloride concentration inside the concrete is low. The surface chloride concentration might be high, but if the diffusion is slow and the chloride concentration inside the concrete is low, sufficiently low, sufficiently below the chloride threshold value, then essentially it will not affect the service life of the structure. That's what I want to mention. But anyway, if it has been given right answer, then I'll take your answer. But yeah, again, it is a comparison between uh, structure which is not exposed to chlorides versus the structure which is exposed to chlorides. So if that is compared, then surface chloride concentration will have a uh, thing to do about it. But in case a structure is we are comparing two structures which are exposed to chlorides in the same manner, if the if one structure has a high chloride threshold, which is sufficient enough for it to so that the initiation phase is greater than that of the design life. If the initiation phase is greater than service life, then threshold, then surface chloride concentration will not affect it. Of course, chloride threshold has a thing to do about it. A chloride threshold will govern the service life. The chloride diffusion coefficient will govern the, let's say the surface chloride concentration is even low, but if the diffusion coefficient is high, then more and more chlorides will get diffused, and ultimately the chloride threshold will be overtaken. So that will affect the service life again. Anyway, I hope that is clear what I wanted to mention. I'll again recheck the answers as Dr. Satish showed. Yeah, so this is a picture I have taken again from Bartolini et al. 2013. I want to uh, so I want to explain this. So this is D app is the diffusion coefficient, and this plot, I mean, this graph plots the initiation time, which is the initiation of corrosion in the y-axis versus the cover thickness in the x-axis, as I've already mentioned as well. If the cover thickness is high enough, so I'll take some time over this graph to explain this. So as you can see, this let's say the plot, the curve one, curve two, and this is the curve three. The one curve for the first curve is has a lesser diffusion coefficient than the second curve, and which is the lesser diffusion coefficient than the third curve. And for a given cover thickness, let's say around 20 mm cover thickness, if you can see the initiation time for curve one, which has the lowest diffusion coefficient, the initiation time is around 40 years. While that while that for the second curve, which has a mediocre diffusion coefficient of 10 to the power minus 12, which lies between both 1 and 3, it is hardly between 0 to 10. And if we compare the same for the curve 3, which has the highest diffusion coefficient, it is almost nil. So for a given cover depth, we can see that the initiation time is directly related in an inversely related to the diffusion coefficient. The higher the diffusion coefficient, the lesser is the initiation time. Now, if you take the initiation time to be a constant value. So if I compare, not this point, probably around this point, a 10, if we compare a 10 years of initiation time, we'll find that the concrete that has the lesser diffusion coefficient, the lowest diffusion coefficient will only need a cover thickness of 10 mm as compared to the mediocre diffusion coefficient curve 2, which will need a cover thickness of around 30 mm as compared to the curve 3, which will need a cover thickness of around 75 mm. So if you want to have the same initiation time with different diffusion coefficients, you need to vary the cover as required. So as I mentioned, if again, let's say we want the initiation time to be 50 years, if we provide sufficient cover for concrete which has even has a high diffusion coefficient, then we'll be able to lengthen the corrosion process and restrict it to a certain period. Right? I hope this diagram was clear. All right. Moving on to the fifth question. Passive film of a metal is a very thin layer of its oxides or hydroxides. Say initial corrosion products. We have already discussed this. Can somebody answer to this question?
True. This is true.
Right. All right. Thank you, Dr. Satish. Yes, as we have already discussed, this is a true statement. The passivating film around the metal or the steel is a very thin layer of its oxides or hydroxides, which usually form when it comes in contact with the surrounding environment. And this passivating film protects the steel or the metal from getting corroded. All right. Moving on to the sixth question. In steel concrete systems, corrosion can occur even in the absence of oxygen. True or false? Can somebody answer to this question?
This is false because corrosion
Because,
cannot take place in the absence of oxygen. Both moisture and oxygen are required.
right. This we have also discussed in the last session as well. Thank you, Dr. Satish. So we have also discussed in the last session as well. There is a question in the practice assignment 0, which mentioned that what are the essential conditions for corrosion to occur inside concrete? And we had discussed that water and oxygen are the essential components for corrosion to occur. But presence of electrolyte like salts can accelerate the process, but only essential components for corrosion to occur is water and oxygen. Of course, there are different types of other different types of corrosion like stray currents, induced corrosion, or hydrogen embrittlement, or those kind of stuff. But anyway, the absence of oxygen in the absence of oxygen, corrosion cannot occur inside concrete. Okay, moving on to the seventh question. It was regarding typical in-service pre-stress can reduce the chloride threshold of pre-stressing steel. True or false? And why? This is a good question. Yes, can somebody answer to that?
True,
True. Okay.
because
Why?
because under stressed condition, corrosion processes faster. So it is a case of very high level of stressing. Obviously, at lesser chloride level, corrosion can be initiated.
Right. Okay. Thank you, Dr. Satish. Yes, as he has rightly mentioned, the presence of previously induced stress can always increase the risk of corrosion because even with a lesser amount of chloride than the chloride threshold, which essentially is the reduction of the chloride threshold. So even with a lesser amount of chlorides, the corrosion can take place. And also additionally having inducing stress to the steel can also lead to certain type of um, so it'll also affect the surface of the steel by um, c- creating certain kind of defects, or it'll also affect the surface of the steel by producing certain deformities or irregularities on the steel surface, which will again promote the corrosion process um, uh, by creating a cathodic and anodic kind of a reaction on the steel surface. So yes, typically in-service pre-stress can reduce the chloride threshold of the pre-stressing steel and hence make it prone to chloride-induced corrosion as well. The eighth question was, cold, twisted, deformed or CTD rebars have higher corrosion resistance than mild steel. True or false? Yes, somebody wants to answer that question. Cold, twisted, deformed CTD rebars have higher corrosion resistance than mild steel. Is if it is true or false? Yes.
It's false.
It is false. Why?
Professor Pillai has worked on that. He has a paper.
Okay.
Uh, in case of cold twisting, resistance decreases, corrosion resistance decreases. He has
Okay.
compared mild steel and CTD. He came out with the conclusion that in case of CTD, more energy is imparted and
Right.
corrosion resistance decreases. That is his finding in his paper.
Right. Right. Thank you. Thank you, Dr. Satish. Yes, he has, as he has rightly pointed out. So whenever we are making something, whenever we are manufacturing something using an industrial process from a raw material, so the raw material which lies in its natural state, sorry, raw material in its natural state has the lowest form of energy, right? Now, industrial processing adds energy, to the material to give out a finished product. And regarding the steel process, mild steel requires lesser energy to produce than these high carbon steel bars, or in case of this question, the CTD rebars. So once something has a higher energy state, it will again want to come down to its lowest possible energy state, and therefore, which has the material that has a higher energy state will have a high risk of corrosion. That is, in this case, CT rebars are more prone to corrosion. Apart from this, we have also seen in the lectures or in different books as well, the inclusion of more carbon in the steel will also reduce the chloride threshold, and hence the corrosion resistance is also reduced. This is to explain this concept. I've taken this pictures from the book again from by Bertolini et al. 2013. So as you can see, these are different types of stainless steel, 316L and 304. Sorry. And this is carbon steel. So for a pH, so they have shown like with the increase in pH, what is the chloride threshold that is required for different kinds of steel? That is, I mean, with the increase in pH, what is the chloride threshold that can be allowed for different kinds of steel? And you can see that, yeah, of course, with increase in pH, the chloride threshold increases. But while the stainless steel lies in a higher chloride threshold regime, high carbon steel lie in a very low chloride threshold regime. So the steel with higher carbon will be more prone to corrosion. All right. Moving ahead to the next question. The question number 9, stopping chloride ingress after corrosion initiation cannot halt chloride-induced corrosion provided oxygen and moisture is still present. Right? I want to underline this last line, provided oxygen and moisture are still present, true or false? Yes. Anybody wants to answer this question? Oh, somebody else
It's
has
true.
joined, I guess, Subhajit Kamakar. Yes, Dr. Satish. Yes, it's true. Okay.
Uh, it's true
Okay.
because once chlorides are in, these will keep on interacting and corrosion process is on. It cannot be stopped unless we go in for very special technique like cathodic protection, etc. It
Right,
cannot
right,
be stopped even if oxygen moisture is there.
right. Thank you. Uh, if so, even if oxygen and moisture is not present, will it take place? Do you want to say that?
Provided oxygen moisture are still present. Yes, it will take place if oxygen and moisture are absent.
It will also
You
take
know,
place.
oxygen and moisture are required.
It is required.
But
Yes.
once chloride-induced corrosion is initiated and oxygen moisture are both present, so process will go on. Corrosion
Right,
process
right,
will go on.
right. True. Thank you. Thank you, Dr. Satish. So ideally speaking, if oxygen and moisture are absent, then the cathodic reaction will not take place, in which the oxygen gets reduced and corrosion cannot happen, even if there are chlorides inside. Even if there are chlorides inside the concrete. But this is the ideal case. In no case you can prevent the concrete or the structure from getting exposed to oxygen and moisture at all. You cannot insulate the concrete totally, ideally, from oxygen and moisture. So since oxygen is and moisture both are present in our environment, it will get I mean, the concrete structure will get exposed to both oxygen and moisture, and hence, even if we try as much as we can, we cannot prevent the corrosion by restricting the oxygen and moisture. So therefore, oxygen and moisture will be present in practice always. So in practice, oxygen and moisture are always present in varying concentrations. So therefore, once the chloride in initiation has take place, the corrosion initiation has take place, stopping the chloride ingress will not halt the chloride-induced corrosion unless, as Dr. Satish has already mentioned, there are certain techniques by which we'll be able to restrict or rather elongate the corrosion process. But unless we do that, no, we won't be able to reduce the corrosion by stopping the chloride ingress. All right. Moving on to the last question. The 10th question was presence of irregularities, uneven surfaces, small gaps, etc. at microscopic level on the steel surface can cause crevice corrosion even without the presence of chlorides. True or false? Can somebody answer to this question? This is the last question of the session, and I would encourage others to take a guess or rather answer to the question, except from Dr. Satish? Yes. Subhajit Karmakar has joined. If you want to answer to the question, raise your hand. I'll allow your mic and you can speak. All right. Dr. Satish, you want to answer to this question?
It is
No?
true.
Okay. Yes.
Crevice corrosion can take place even in the absence of chlorides
Right.
because of
Okay.
irregularities, etc.
Right. And
Non-uniformity.
thank you. Thank you. Yes, due to the presence of irregularities and uneven surfaces, so on the steel surface, this crevice corrosion can take place. And so essentially, like I guess it has also been shown in the lecture sections as well, taken by Dr. Radhakrishna G. Pillai. So there
That's right.
is the
That's right.
presence of, yeah, there is the presence of mill scale on the surface of the rebar while it is produced. So this is the mill scale. And this is a irregularity in the or inhomogeneity in the steel surface. This is the rebar, right? And what happens is, so in this point, if I enlarge this point, it has also been shown in the lecture as well, but I'll again explain it here. In this point, what is happening is there is, due to this irregularity and due to the inhomogeneity between the material, this crevice kind of a thing occurs in this region at this location, and this will cause a corrosion even with an absence of let's say chlorides. So this will so the corrosion will start in this crevice and it will start getting deeper into the rebar region. So this is known as crevice corrosion in the case of this happens in the case of presence of irregularities or inhomogeneities on the surface of the metal. So the answer to this question is true. Presence of irregularities can cause crevice corrosion even without the presence of chlorides. And this is the last question of this assignment of week one. Thank you. I would like to take questions or any doubts that you might have related to the week one lectures. Uh, we will be discussing the week two assignment and the week two lectures in the coming session. But if you have any doubts related to the week one lectures or to this assignment that we have discussed today, yeah, you can raise your hands and I'll allow your mic and you can ask. The session is till 8 p.m.
Well explained by you.
Thank you, Dr. Satish.
Okay. Can we take leave?
Yeah, sure. If you don't have any
Thank you.
doubts or any discussion that you
Okay.
want to have,
Thank
you can leave.
Thank you.
Thank you, Doctor. Anybody else? You have any doubts or you want to discuss something? Yes, anybody? Do you have any doubts? Manisha, Aishwarya, Subhajit, only three of you are present. Do you have any doubts related to the lectures of week one or related to anything that was discussed in the last discussion session or today's discussion session? You guys can raise your hand and ask your questions. All right, I'm muting myself. Unless you guys are free to go, I mean, there is no more discussion of any questions anymore today, unless you have any questions. If you have any questions, raise your hand so that I'll unmute myself and will discuss. For the time being, I'm muting myself. Yes, Bijendra Singh has raised his hand. Yes, Bijendra, you can unmute yourself and speak. Bijendra, you're still muted. You have to unmute yourself to speak. I've allowed your mic. Bijendra Singh, can you listen to me? Am I audible? Can you hear me? If you can hear me, I've allowed your mic. Please unmute yourself and speak. You can also use the chat box to put your query or question in that. If your mic is not working for some reason, you can put your query or question in the chat box and I'll answer to it. I've allowed your mic, Vijendra, in case you want to speak or you want to put something in the chat, you can do that. Mr. Vijendra, I have allowed your mic. You can unmute yourself and speak. You can keep your video on as well. It's fine. Yes, Vijendra, we can hear you.
Yes, sir.
You want to say something? You had raised your hand.
Sir, sound low sound.
You're not able to hear me?
Yes.
Uh, I guess I am audible to everyone else, but I mean, they confirmed that I was audible. Am I audible to you now? Mr. Vijendra?
Yes, sir.
Can you hear me now?
Yes, yes, yes.
Okay. आपका कोई सवाल
Okay,
है?
sir.
Do you want to ask something?
सर जी
कुछ
सर, इंग्लिश इतनी बढ़िया नहीं है सर मेरी, जो
बताइए,
कुछ
क्या
समझ पाऊँ
पूछना है
सर।
आपको? हिंदी में बताइए, कोई दिक्कत नहीं है।
सर अभी ज्वाइन हुआ, अभी कुछ पता नहीं चल पा रहा मुझे सर। वीडियो नहीं मिल पा रही, एक तो आपके सर मुझे नजर नहीं आ रही कहाँ से आएगी।
अच्छा जी, आप अपना आपका वहां पे वीडियो कैमरा नहीं, मेरा वीडियो आपको नहीं दिखेगा। तो
जी
मैंने
जी
एक्चुअली इसमें वीडियो अपना बंद किया हुआ है, बट आपको मेरा स्क्रीन दिख रहा होगा, है ना?
जी 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 जी
जी,
सर, जी
मेरा
सर।
लेक्चर का स्क्रीन दिख रहा होगा। और ये जो आज का जो डिस्कशन था, आप शायद लेट ज्वाइन हुए हैं। ये 6 से 8
जी जी
बजे
अभी
तक था। और ये हर
जी
शनिवार
जी
को 6 से 8 बजे तक के लिए सेशन होता है, डिस्कशन और डाउट क्लियरिंग होती है। तो आज हमने
जी सर।
सेशन वीक 1 का जो असाइनमेंट था इस कोर्स का, उसके क्वेश्चंस को डिस्कस किया है।
जी सर।
और ये जो आज का सेशन है,
जी
ये मैं उसको यूट्यूब पे अपलोड कर दूंगा। और इसका लिंक आपको NPTEL भेज देगा या फिर मैं आपको नेक्स्ट सेशन में इसका लिंक दे दूंगा। तो आप एक और बार, आपको
जी
अगर
सर।
चाहिए तो आप और एक बार जाके भी देख सकते हैं। और ये जो आज के जो प्रेजेंटेशन के
ठीक सर,
स्लाइड्स है,
ठीक।
इसका भी फोल्डर का लिंक मैंने चैट में शेयर कर दिया है, आप चैट में जाके देख सकते हैं। ठीक है।
ठीक। जी जी जी।
ओके ओके, थैंक यू।
ओके
और
सर।
कुछ? ठीक है।
नमस्कार नमस्कार।
ओके, थैंक यू।
All right, we're closing the session for today. We'll have another session in the coming week on Saturday between 6 to 8 p.m. Thank you.